All right, so today we're going to look at our final conic section, which is a hyperbola, and that's going to be a slice through that double inverted cone that goes through both sides of that cone. So we can kind of see that image right here. So when we look at our hyperbola, it's going to have a lot of similar anatomy to an ellipse, but sort of constructed in a different way. So we always start with this locus definition, which is the set of all points in a plane. And then we have different constraints on it. And for a hyperbola, it's the set of all points in the plane in which the difference of the distances. When we did the ellipse, it was the sum of the distances. So the difference of the distances from two distinct fixed points, the foci or foci, is constant. So this one is slightly different. And when we look at the hyperbolas, we sort of orient them the same way ellipses are. There's horizontal and then there's vertical. So we're going to start this time with the equations for each one and then sort of construct them so we can understand where the A, B, and C values are and how they're related to each other, because it's different on an ellipse and a hyperbola. Okay, so what we've got here on the left is a horizontal ellipse. And it's horizontal because what we've got here is this is called the transverse axis right here. And at the endpoints of the transverse axis, we have our vertices, just like we did on the ellipse. And then this distance is still called A, your distance from your center to your vertex. So A is your distance from center to vertex. And then we kind of have the same thing going on here, where we have a B value, and then this is called, right here, these aren't called vertices, but this right here is called the conjugate axis, so we'll write both of those. Conjugate axis. And that's kind of like the minor axis. It's secondary, like in the ellipse we had a major and a minor axis. Here we have the transverse axis and the conjugate. And the reason they're not called transverse, or they're not called major and minor, is because the A value does not have to be larger than the B value on a hyperbola, like it does on an ellipse. So we've got our transverse axis right here. And then you see we kind of have this rectangle that's drawn. Instead of drawing those and connecting them with an ellipse, we sort of make a rectangle, and then we identify these asymptotes. Oh, let me label this. This distance is B. So that again is your distance, center to endpoints of your conjugate axis. So as I was saying, then we have these asymptotes on here. So these asymptotes are going to serve as boundaries for graphing. And so when we sketch these, we put the A and the B values on, we make this little rectangle, and then through the corners of the rectangle, we sketch our asymptotes. And those help guide us to see what kind of shape this is. The closer, or like the more narrow they are, we're going to see a narrower hyperbola branch on each side, and the wider they are, we're going to see a wider one. So the last thing we have is A, B, and then of course C. Now here's the key difference. On a hyperbola, our focus points do not lie inside the vertices, they lie outside the vertices. And so our C distance is again your center, distance from center to vertex, center to a focus. And so when we look at these, we can see that the C value is going to be the largest of all these values, right? So the relationship between A, B, and C is going to be a little bit different. And we'll talk about that in a minute. So I like to think of this kind of like an ellipse that's turned inside out, where the focus points are no longer inside of the vertices, contained inside, they're now outside. So our transverse axis has a length of 2A, kind of like our major axis, but we want to remember that A does not necessarily have to be bigger than B. It can be, it may not be, it could also be equal to B. Okay, so here's how a horizontal ellipse equation looks, or horizontal hyperbola, sorry. All right, so for a horizontal in standard form, x minus h squared, and then instead of addition, subtraction, and then y minus k squared in this numerator, and then equals 1, and then a squared over b squared. So same things, our center is hk, right? So let's not forget that, center is hk. And then our a is distance from center to vertex, b is the distance from the center to the endpoints of your conjugate axis, and c is your distance from center to focus. The vertical ellipse equation looks a little bit different, so I'm going to go ahead and write it, and then you can kind of examine what is different about it. I keep saying ellipse, but I mean hyperbola. Vertical hyperbola. And so that one's not going to start with x this time. It's going to start with y minus k squared, still over a squared, and then minus x minus h squared over b squared equals 1. Okay, so keeping in mind that a doesn't have to be larger than b, when we look at these equations, the difference between them is the horizontal one starts with that first term, that positive term before the minus sign, as the x squared, whereas the vertical starts with the y squared. And then a is always the value underneath that first term. So again, it doesn't have to be the larger one. All right, so this would be a good time for you to pause the video and see if you can sort of identify the same features that we did on this horizontal hyperbola as you see on the vertical one. Like where would the center be? Where would the vertices? Where are the endpoints of your conjugate axis? Those sorts of things. So I say go ahead and pause that right here and see if you can construct that, and then let's check. Okay, if you're back to check, we would go ahead and label these things like this. These would be my vertices. Now my vertices are above and below each other. They're in a vertical line. That's why this is a vertical hyperbola. We've got our transverse axis to connect those. And then we've got these right here, and this is my conjugate axis. And then this value right here is b. Distance from your center to your vertex is a. Your focus points, until we calculate what c exactly is, we don't know where this would be, but we do know it would be somewhere outside of the vertices. So these would be like our focus points. And then that distance from center to focus would be c. We have these asymptotes, right? And these asymptotes are kind of our boundaries. And all we do when we plot these is we make this little rectangle with our a and b values, connect the diagonals to draw those asymptotes, and then we just have the one point on the vertex that we graph, and then we graph a curve that doesn't go beyond those asymptotes. Okay, so speaking of those asymptotes, we kind of want to understand how we write the equations for them. So on the horizontal, we're just going to do a line, and we're going to have it kind of in point slope form. And so when I look at this, if I look at the first one, the rise over the run, if I were to get from my center out to this point right here, so if I'm trying to get from here to here, I would rise B and run A. And so when I think about this, my slope then is up B and over A. It could also be up B and back A. So when we go to write our equation for the asymptotes, B over A is going to be our slope. And so then we're just going to do y minus k equals plus or minus B over A x minus h. So this is from way back, but this is basically point slope form, and we have our y and x, h and k is going to be the point we use in our point slope form, and then the slope is B over A. You don't have to memorize these, they'll be provided, but it's nice to be able to understand them and not have to look back at a formula chart to do this. So you want to sort of be able to understand without looking at the formula, is the slope going to be B over A, or is it going to be A over B? When we look at our vertical hyperbola, we're going to rise A and run B. so our slope is going to be a over b here. But we're still going to have our center, the hk, be the point we use in our point slope form. So y minus k still equals plus or minus a over b x minus h. Again, you don't have to memorize these, but it's good to understand where they come from and why it's a over b on the vertical versus b over a on the horizontal. All right, so the last thing we want to summarize is that the relationship we talked about between a, b, and c is different. On an ellipse, a was always the biggest value, and we had that formula c squared equals a squared minus b squared, and that determines the relationship between a, b, and c and where the focus is, or the foci. When we do a hyperbola, that formula for the foci is very similar, but not the same. So it's going to be c squared equals a squared plus b squared. So when we're talking about the foci, we use that nice Pythagorean theorem, c squared equals a squared plus b squared. And I kind of like to think about it this way. The formula to find the foci has a plus in it, but our equations are subtraction in a hyperbola. In ellipses, it's the reverse. In ellipses, we're adding the two terms in our standard form for our ellipses, and then we're subtracting a squared and b squared. Okay, so because of this relationship, something we need to understand about a is it may or may not be greater than b. So a may or may not be larger than b, or be greater. And it's true that they could also be equal to each other. So you really need to sort of undo the relationship that you understood before in ellipses, that a is always bigger than b. That's not the case here. So sometimes our a value might be bigger than b, smaller than b, could be equal to b. Okay, so let's try and sketch a hyperbola real quick and see if we can identify all the pieces and put it together. So the first thing we want to do is establish whether this one is horizontal or vertical. So we want to establish the orientation. So let's talk about that. Now, it doesn't have to do with the a value and b value anymore. It has to do with what's the leading term. And so since this starts with a y squared, the y squared is the positive term, then that's going to be vertical. And then we can establish our center. Now, this can be a little bit tricky, so you want to remember that this is the y minus k squared, and this is the x minus h squared. So our center, most people kind of read left to right, and they say, oh, it's 0, -1, but actually it's -1, 0. All right, so -1, 0 is going to be where we kind of base everything from. And then remember, our first term contains a squared, and our second term contains b squared. So then a would be the square root of 9, which is 3. B would equal square root of 4, which is 2. Okay, so I can use that right now to go ahead and construct that rectangle that we're going to use to draw asymptotes. So since it's vertical, and since the a is under the y, I'm going to use that, and I'm going to go vertically up 1, 2, 3, and then down 1, 2, 3. So these are my vertices. They're above and below center. And then we're going to make the endpoints of the the conjugate axis. We're going to go use our b value and go right 2 and left 2. And then we're going to go ahead and sketch that rectangle. That rectangle is going to help us draw our asymptotes. All right, so then I can kind of draw like this, and I'm going to make, you can even replicate that slope, up 3 over 2, up 3 over 2. There we go. So I can do the same thing this way, and that can help me draw this line nice. And then same thing in this direction. All right, so I kind of keep that pattern going, and here's my asymptotes. And then the vertices are already plotted, and so then we just draw our hyperbola as a curve that connects through the vertex and approaches the asymptotes, but doesn't reach them. So there's not a whole lot of precision about the rest of the points. It's just the vertex, and then you use the asymptotes as your boundary. Okay, so we'll pick up from here. We're going to identify a few features about this hyperbola, but we're going to do that in the next video. So go ahead and move to the next video.